Welcome to lesson 5. So in this lesson, we're going to look at two sample T procedures. So this is doing hypothesis tests and confidence intervals in a scenario where we have two completely separate groups that we want to compare. So maybe I want to compare the average height of all OSU students and all U of O students, that kind of idea. So here is an example, should be a throwback to last week. We have a researcher, they're comparing two different thermometers on 6 different days. So what they're doing is they're saying day 1, here's the temperature, and they're using 2 different thermometers. Day 2, here's the temperature using 2 different thermometers. And ideally, these thermometers should agree. I've done a similar experiment with scales and weights. But the researcher wants to know if the 2 measurements give the same reading on average. It's definitely really important if one thermometer is always a little bit high and one's always a little bit low, you might want to see if it could be recalibrated. It might be worthwhile. You can assume the populations are normally distributed. So use a 10% significance level. So we're not going to have to perform the whole test. This question is asking, calculate that average difference. So here, specifically, it's going to be temp 1 minus temp 2. So like here, that would be positive 0.2. For day 2, looks like it would be negative 0.6, and so on. And there are 6 differences. Once you get those differences, find the average of them. So when you do that, you find the 6 differences and you take the average. The average difference is going to be negative 0.35, and degrees, probably Fahrenheit if it was taken here in the US. So units are going to stay important. What this means, this negative value, means that the temperatures taken with thermometer 1, they're going to be on average a little bit lower than on thermometer 2. Different question. It wants the 90% confidence interval. It said 95. Not sure why. If you look here, it says 90% here. So I'm going to write out what I know. So for starters, the sample mean is negative 0.35 degrees Fahrenheit. And then the standard deviation is going to be 0.332. That's also degrees Fahrenheit. The number of pairs that I have, that's 6, which means I'm going to have degrees of freedom 6 minus 1, that's 5. And then I have to figure out, okay, well, my T-star. So I need to figure out my T-star for a 90% confidence interval when I have 5 degrees of freedom. It's going to be 2.015. And that's going to come from the T-table. So, for example, sorry, it's a little overlaid. I'm going to look at the degrees freedom 5 row, and I'm going to match it up with the column that goes with 90%. And that's going to give me 2.015. So there it is. So, plugging in x bar d plus or minus, I have my T star times SD divided by the square root of ND. This is all a matched pair scenario. I now have all the numbers to plug in. So that's that negative 0.35 plus or minus 2.15 times 0.332. No, I did not calculate this in my head. I threw this into a calculator to get that. Divided by the square root of 6. And I end up getting, give this a try first, B. So negative 0.624 degrees Fahrenheit to negative 0.076 degrees Fahrenheit. So it looks like thermometer 2 is fairly consistently giving lower temperatures than thermometer 1. Oh, sorry. Thermometer 1 is giving lower temperatures than thermometer 2. So looking here, I have my confidence interval from negative 6.24 degrees Fahrenheit to negative 0.076 degrees Fahrenheit. We want to decide what conclusion would we assume from a two-sided pair t-test. So remember, by default, we're going to say, hey, that difference, unless it's a really weird scenario, it's pretty much always going to be 0. So if the two thermometers on average were giving the same reading, the average difference would be 0 degrees Fahrenheit. The alternative here, if it's two-sided, is that it's not equal to 0. Either way, my null or claimed difference is 0. So I want to see, hey, is 0 in here? Because if the null hypothesis is claiming that average difference is 0, if 0 is in there, our answer is going to be, well, maybe. But if 0 is not in there, we're going to go, we don't think 0 is that average difference. We think that average difference is something other than 0. So looking at these two answers, well, these top two answers, we would reject the null at a significance level of 0.10. That's saying, hey, we don't believe the difference is 0. Which we wouldn't, because 0 is not in our interval. So this one does look good, but let's read through the second one. There's no evidence the mean difference is not 0. This would be true if 0 was in our interval, but 0 is not in our interval. We actually have good evidence that 0 is not the mean difference. So I would go with A. So type of procedures, so building up from where we've been coming from last week into this week. So we had a one sample t-test. That's where we want to make a statement about a population mean, but just one. So maybe I want to know the average tuition cost for all OSU students, or the average, number of credits all OSU students are enrolled in. Something like that. And then we move to matched pairs t-test. So this is a scenario where maybe you have before and after, pre and post, or you have dependent observations in some way or another. Like maybe you're doing a twin study in twin 1 and twin 2, that kind of thing. So you're comparing two dependent populations. So exactly one from your first population is matched exactly to one from your second population. They're perfectly matched. You're not going to have folks that are matched to more than one. And you basically end up doing a one sample t-test on the differences. So instead of taking sample 1 and sample 2, you take the differences and then run a t-test on those differences. Usually testing them to see, hey, is it different than, greater than, or less than 0? But this week, so week 3 is getting at this question. Suppose I want to compare the average of two separate groups. So I have two separate populations, and I want to compare their averages. We're going to now need to use a test called the two-sample t-test. Two samples because it implies that I get two samples from two populations that are totally separate from one another. So two sample problems. We're going to have the scenario where we have population 1, population 2. Note, if you use the labels 1 and 2, you should have labeled what 1 is and what 2 is somewhere, because it's very, very easy to confuse what order you're subtracting in. So it's very important to keep track. Otherwise, you're not sure which mean is higher than the other. And usually, you not only want to know if they're different, you want to know which one's bigger or which one's lower. So we're combining those two parameters. So you have mu1 from your first population and mu2. Now the parameter of interest for us is mu1 minus mu2. And it's okay to do it the other direction where it's mu2 minus mu1, but you need to be really clear what 1 is and what 2 is. So we're going to be looking at our parameter of interest is this difference in means. So things to note is it. So my goal, compare 2 treatment means or population means. So paired t-test, you're talking about a mean difference because you're looking at the average of the differences. If you're looking at a 2-sample t-test, you're looking at the difference in means. And they absolutely are different from each other. So you're looking at, hey, what is the difference between mean 1 and mean 2 versus what is the average difference? So conditions. We're going to have conditions just like we have for any Z or T methods that we've used so far. So our first right here is the populations or samples are independent of one another. So what this means is whoever I am sampling from population 1, they are not candidates to also be in sample 2, right? So the idea is I cannot double dip. You don't want to be looking at groups that you know are dependent. So maybe I don't want to look at sample from OSU students and then sample from OSU freshmen, right? Because the idea there is there's a lot of overlap. I could have freshmen that are in both groups. Those aren't 2 separate groups. You need to have 2 completely separate groups. Samples obtained using a random mechanism. So this is important in the sense that we need to know, was there random sampling? And if it's an experiment, we also want to know, hey, was there random assignment to treatment groups? And then populations, we want to know, are the populations involved normally distributed? A lot of times we won't necessarily have the benefit of knowing that, but we want to know at least like, hey, is our sample size going to be big enough for that central limit theorem to kick in? We definitely want, hopefully, for them to be similarly shaped. You don't want to have two samples from 2 populations that are totally differently shaped and you have small sample sizes. That makes us really, really sad. It makes us nervous to compare those 2 groups that way. So absolutely, we love it when the populations are normally distributed, but in general, we want to know, is the sum of the sample sizes going to be at least 30? So then, here population means mu1 and mu2 are unknown. I mean, this one's pretty much, I wouldn't say that this is so much of a, I would definitely describe it like, we want to know they're independent. We want to know random here, and then probably here so much. Because if we know the population standard deviations, there are Z methods we could use. It's really, really uncommon though. It's really uncommon for us to be in a situation where we know sigma 1 and sigma 2. It's not something we usually have the benefit of having. So, I mean, this is generally true. If you know mu1 and mu2, you're not going to have to use T methods because you know what mu1 and mu2 are already. But yeah. Conditions for comparing 2 means. So 2 sample T procedures for a difference in means. So the population, you want to compare 2 means, we take their difference. So it's a difference in means. Mu1 minus mu2, it's okay to use other labels besides 1 and 2. Just make sure that it's clear what each subscript. So you could say, oh, mu of treatment 1 minus mu of treatment 2. You can write more than just 1 or 2 in there. And so the difference in the means, that's our parameter of interest. So this whole thing, so even though there are 2 parameters in it, the entire thing itself is a parameter. Then when we deal with samples, we want to make a claim or estimate if we're going to use the sample versions. So if we don't know what mu1 minus mu2 is from the population, we're going to use the sample mean from sample 1 minus the sample mean from sample 2 as our point estimate. This is where we're going to start. If I want to find this right here, I'm going to use the difference in the sample means. And here is how we will set up our hypothesis tests as far as our hypotheses. So I prefer to use these bottom notations because it allows me to see what that null or claimed difference is. But the idea is saying, hey, you know what, a two-sided mu1 and mu2 are equal to each other. By default, that's the assumption. And our alternative will say, well, no, they're not equal. So this is the scenario you want to know if there's a difference. Maybe you just want to see if one's different from the other, and you don't have a specific claim like, oh, I think that, you know, the mean is higher in population 1 versus 2. That's when you go with a two-sided. You have a less than, you have a greater than. Once again, I really prefer, I'm going to continue to use this bottom version. So you see mu1 minus mu2 is equal to 0, so you see that null claimed difference. The only difference here is if you went ahead and added mu2 to both sides, you would get back to here. So they are mathematically equivalent there. I just prefer being able to read it the bottom way. So when you want to test to see if there's a difference versus when you think mu1, so the mean in population 1 is lower than population 2 versus when it's greater. So two sample t procedures. So we're going to have, it's going to be a t-test statistic. And so our point estimate minus the claimed difference, usually going to be 0 over, and now it's going to be a little more complicated than our standard deviation over our square root of our sample size, because we have two sample sizes, right? So x bar 1 minus x bar 2, that's that observed difference of the two sample means. This is our point estimate from the samples. So delta 0 or delta naught, it's the hypothesized value for the difference. Almost always it's going to be 0. I do occasionally see a scenario where it isn't 0, but it usually is going to be 0 because people usually want to say whether or not there's a difference. Now, if they want to say, hey, you know, let's test to see if the mean in population 2 is greater than 5, well, then that value would be 5. So then S1 squared and S2 squared, those are our sample variances. So the sample variances, that's just the standard deviation squared. So standard deviation 1 squared, and standard deviation 2 squared, those are variance 1 and variance 2. So then N1 and N2, those are the respective sample sizes. So you can take N1 from population 1, and that's your sample from population 1. And then you can do the same for population 2. You can have different numbers. So unlike with the paired t-test, you have to have the same exact number in both groups. Here, this is not required. I can have 15 in sample 1 and 30 in sample 2, and so on. You can really change it up. A lot of times folks like to have equal sample sizes when they can, but it's not always doable. And especially in scenarios where one population is a lot bigger than the other, sometimes it's very difficult to do that. So the two sample procedure for a confidence interval, so it's going to still be your point estimate. So the difference I observed in the sample, I like to put parentheses around here. It's not necessary, but it reminds me to do the multiplication first. Plus or minus, so then there's t star. So your critical value t star, which we get from a t-table. And specifically, a t-table with, if you're going to use a t-table, we're going to use, this is our conservative may not be space there. Conservative degrees of freedom. So you're basically going to take the smallest sample size and subtract 1. So if I had a sample of 10 or 15 and 30, I would use the sample of 15. So 15 minus 1 is 14. That kind of idea. So just take the smallest sample size and subtract 1. And then this is my standard error here. And it's going to, so that's that standard error of the approximate sampling distribution of x bar 1 minus x bar 2. So we kind of talked about how the sampling distribution of x bar was when we were only collecting from one sample. This is what we're doing when we're collecting from 2. So performing a significance test in 4 steps. So we're just kind of breaking up into 4 steps. So the first place to start is to state what your question is. What is the question we're pursuing? What is the question we're trying to answer? It's not trying to answer it yet, but you have to put into words what is it that we're asking. If it's a yes or no question, hypothesis test. In general, if it's more open-ended, like, hey, what is the average height? That's going to be a confidence interval. So what is the practical question that requires a statistical test? This is going to be, in generally, like, it's going to have words like, is the average different than or higher than or something like that. It's going to be posed as a yes or no question. Then for our plan, we want to identify what the parameter of interest is. So for a 2-sample t-test, it's going to be like mu1 minus mu2, and then you're going to have to be able to describe what that is in context. Then we're going to state our hypotheses and state the significance level. If it's stated already, it's not really in the selection. That's kind of misleading. You have to use the significance level like provided. However, when we don't provide one, it's usually okay to go with like 0.05. That's a good default. Things to note, if you have a confidence interval and it doesn't state your significance level, you can usually make sure that, hey, the two add up to 100%. Like if you have a 90% confidence interval, it's safe to assume that you'll use a 0.10 significance level because 0.10 and 90%, they add to 1. So then solving, you're going to check conditions because if it's not even appropriate to use a t-test here, we really have questionable results in the first place. Then you calculate your test statistic and find that p-value. And then you have to wrap it all up. So you have your conclusion. So make your conclusion. So that's using that like 2-part conclusion. And I can post I think we have a couple of 2-part conclusions that we use in this lesson. But I can post a more general template as well. So an example that we're going to use, we have some medical researchers. They're looking at a new weight loss program, and they want to know, so they know that their program's effective, but they want to know, okay, well, is this new program, how does it compare to the old program, essentially? So they divvy folks up into treatment A and treatment B. So if you were so this is the new one. If you're put into treatment A, it's a web-based app. And there's support on there, but it's all through an app. It's all web-based. Treatment B is in person, so this is definitely pre-COVID days. And so you have a support group in person, and you have in-person nutritional counseling. So basically it's app-based versus in-person based. So things to note is it's a lot less expensive to apply treatment A using this app. So if they don't have evidence that there's a difference, they want to use the cheaper one, right? So unless there's evidence that one is better than the other, like unless they find evidence specifically that treatment B is better, they're probably going to want to use treatment A because it's cheaper to do. And this is actually something that shows up a lot of the time, that a lot of folks are like, hey, as long as, this isn't, worse than this one, we're going to use the cheaper option. Just look at generic drugs. They do that kind of thing all the time. So we want to test whether there's a difference in average weight loss among the two treatment groups. They don't necessarily assume that one is doing better than the other. So what they do is they have, it looks like they have 39 individuals, and they randomly select that 21 of them are going to use the web-based app, and then 18 of those are going to use the in-person based program. And so they're not informed of the other treatment. So it's not necessarily, they know what treatment they're getting, but they don't know that there is another treatment, is the idea. And so we can assume the groups are assumed to be homogeneous. This is saying we can assume that the shape of the populations are the same. So having, sample sizes of 18 and 21 are going to be okay. That is not too small. And so then after 6 months, they measure the weight loss for all of the participants, so for all 39 people. And so population, they have treatment A and treatment B. You could also reasonably say, oh, well, mu A or mu B. It's totally fine to use mu1 and mu2. Just make sure 1 and 2 are labeled somewhere. That 1 is associated with treatment A and 2 is associated with treatment B. There's the sample mean for both. So they, looks like it was a US study. It's in pounds. Standard deviations, those are also in pounds, but we tend to be less particular about the standard deviations having their units. And then the sample sizes. And as you can see, they don't have equal sample sizes, and that's okay. That's not too big of a deal. It's a big deal if one's way smaller than the other, but this is fine. So stating, and then our plans here, is there a difference between the average weight loss among the two treatment groups? So we want to know, exactly, is there a difference in average weight loss between treatment A and treatment B? We don't have a particular suspicion one way or the other that, hey, one of them is definitely higher. So then my parameter of interest is going to be mu. I'm going to write it mu A minus mu B. That way it's just easier. So this is the difference in mean weight loss between treatment A and treatment B. And I just like to be really clear, treatment A minus treatment B. About the order subtraction. It's a really important detail, and it really comes to get you at the end when you're doing your write-up, because if you don't keep track of which way you're subtracting, it's a really, really confusing write-up. And then our significance level, I feel like here we actually do a 90% confidence interval. So it would be 0.10, but we'll double check. So state the hypotheses. So null, alternative. So looking here, mu A minus mu B. We're going to assume that's 0. And then the units are just pounds. And it is important that if what we're looking at has units like pounds, that we do include them. There are times when it's a bit confusing what the units are, and you can always clarify with us. But in general, if there is a clearly defined unit, you want to make sure you include it. So the alternative, you set it up exactly the same except for the sign. So mu A minus mu B. What goes here is different. And then 0 pounds stays the same. So here, because we don't have one suspicion one direction or the other, say not equal to. So this would be a 2 not equal to. So this would be a two-sided test. What that means is when we find our one-sided p-value, we multiply by 2. So we have a two-sided p-value. And we'll use a significance level of 0.10. So there it is. And I know that wasn't stated earlier. In general, if we don't write what significance level to use, it's usually okay to use 0.05, but sometimes we'll include it later. We'll go, oh, using a significance level of blank, what's the answer? Or what's the conclusion? Or matching it to a confidence interval. So later on, we'll calculate a 90% confidence interval, which goes with a 10% significance level. So now we have to check our conditions. Did we get our samples using a random mechanism? So that's going back to how was this designed. So honestly, these participants probably weren't a random sample, but they were randomly assigned. So ish. I'm going to say yes-ish. They were randomly assigned to the treatment groups. But the volunteers themselves, it sounds like a volunteer sample. So, yes and no. Like, it wasn't a random sample, but it was randomly assigned to treatments. So, what that means is maybe we can't broadly say it about everyone that would participate in this program because they were volunteers, but for the volunteers, for all the volunteers or whatever, we could probably say, hey, you know, we can say that the difference in weight loss was caused by the treatment that they were assigned to. So I mean, it does limit a little bit our conclusion at the end, but it's worth noting that there are two random aspects to it because it's an experiment. So are the sum of my sample sizes greater than 30, or do we know if they're normally distributed? So we know the populations are similarly distributed. We don't know if they're normally distributed. But their sample sizes are 21 and 18, so we have a combined sample size of 39, and that is higher than 30. And then, are the samples independent? So, yes, they're assumed to be independent. What this means is if you are in treatment A, so you have the app, you are not in the in-person group. And if you're in the in-person group, you do not have the app. So unless there are people that are on both, yes, we can say they're independent, that, you know, they are in their own separate groups and they're not talking to each other kind of idea. So then computing the test statistic. So we need all of our information here. So we have our sample mean from treatment A, our sample mean from treatment B. We have our standard deviations. We have our sample sizes. So the big thing here is the claimed difference. This is almost always going to be 0. It's rare that it's not 0. It can be something else, but it's usually going to be 0. So know that on top, usually it's just x bar 1 minus x bar 2. Almost always. So 18.4 minus 22.7 minus 0 all over, so 9.8 squared over 21 plus 12.8 squared over 18. And I have to say, dropping these squareds, forgetting to do the squareds, is probably the most common mistake when entering this into a calculator. So just a caution, it's really, really easy to do 9.8 over 21 and not 9.8 squared over 21. They're also really handy. You can throw in, if you have the information in this table and you have a TI 83 or 84, you can throw it into your calculator and plug it in and it will help you calculate this for you. But you do need to know how to set it up. Anytime we ask you to show us how it's set up, this right here is what we're asking for. We want to know what numbers were plugged in and where. So that's what we'll look for. We'll look for this and then the answer. If you have this set up perfectly correct but the wrong answer, you still get most of the points because you have it set up correctly. It's somewhere in the calculation, like throwing in the calculator, that it got goofy. So let me see. This is not doing your head math, at least not for me. I got something like negative 1.163. And depending on rounding, as long as you're pretty close, if we can tell, like, hey, yes, they plugged in the right numbers, and yes, they got pretty close, we're pretty happy. Now, if you got like 2.4 something, then we're not going to be very happy. So looking here, my t-test statistic was that negative 1.163. My degrees of freedom. So that's going to be my smallest sample size. So smallest sample size minus 1. So we had 18 minus 1. So this is my conservative degrees of freedom. 17. So this tells me what row to use. So I'm going to use the 17 row. And I'm going to try and figure out, since this is perfectly symmetric, negative 1.163, this area would be the same as positive 1.63, this area here on the right. So I'm going to look for positive 1.63 in this line somewhere here. So like here, 1.163 is not between 0.689 or 0.863. So I'm going to keep looking. It's actually going to be between these two. So if I can draw without, there we go. So if this number here, like the absolute value of it, is between these numbers, this means my one-side p-value is between these. Note that it reverses the order there, so my one-sided p-value, it's between 0.10 and 0.15. But then you have to remind yourself, hey, do I want to have a one-sided p-value? Because our alternative hypothesis was two-sided, right? So not equals sign. That means I have to just multiply everything by 2. So I'll get 0.20. I'll get a two-sided p-value less than 0.30. So my two-sided p-value is between 0.20 and 0.30. That's really, really big. So looking here, if I wanted to do this on a TI-83 or 4, you go to that stat button. So you can either enter the entire data set if you have it into there and use data, or, so I mean, you go to tests, you go to 2-sample T test. They also have a 2-sample T interval for later. It's easier if you have that stats. So we just went ahead and entered X bar 1, standard deviation 1, N1, and then X bar 2, standard deviation 2, N2. And then we told it this is selecting the not equals. And then we picked this thing called no, so pooled standard deviations. This is saying no. Basically, this is saying don't assume that the standard deviations from the two populations are equal to each other. The calculation is slightly different. Always go with no, pretty much. It's not usually a good idea to say yes because it only works well some of the time. No works well all of the time. And then, yeah, here's our p-value. So it's 0.2536. So it is between 0.20 and 0.30. So it's a very big p-value. And here's our t-test statistic as well. So before we put into our part summary, we're going to also find the 90% confidence interval. So we need all this information again. We will need a t-star. So looking back, okay, I'm going to want to look at a 90% confidence interval and degrees of freedom 17. This means my t-star for my confidence interval, for a 90% confidence interval, is 1.740 or 1.74. Oops. So t-star is 1.74. I now have everything I need to plug into here. So plugging in 18.4 minus 22.7. And note, having negative numbers just implies that the mean in treatment A is lower than the mean in treatment B, which may not be a huge surprise to us, considering we're trying to figure out if treatment A is as effective. So plus or minus 1.74 times stuff in a big ol' square root sign, so 9.8 squared divided by 21 plus 12.8 squared over 18 and the square root, parentheses. So absolutely feel free to show additional steps. But when we ask for like work or setup, we're looking for this step right here. We want to know what numbers were plugged in and where. If you continue to show us additional steps, if something goes sideways, there's a lot more potential for partial credit. When stuff, like if you just put an answer and it's just wrong, there's no partial credit to give. And that makes us really, really bummed out. So we at least want the setup. You can show the extra steps if you want, but it's really, really important to have this first step. This then, oops, after plugging in, I get something negative 10.57 pounds, because those are still our units, to positive 1.97 pounds. And that's our 90% confidence interval for mu A minus mu B. And it's okay to use the 1 and the 2. It's a little easier for me to keep track that one's for treatment A and one's for treatment B if I use A and B. So, and note here, it goes from negative numbers to positive numbers. 0 is in here. So that kind of agrees with, if we have a big p-value, we're going to fail to reject, so we're not going to conclude, hey, that difference in means isn't 0. We don't have evidence that it is not 0. And looking at this confidence interval, we definitely don't have evidence it isn't 0, because 0 is in there, right? So we don't have evidence it is 0. That's not, we're the prosecution, we're not the defenders, so we just don't have evidence that it isn't 0. So if you wanted to throw this into a TI 83 or 84, you're going to go to the stats, you're going to go to test. If you go down, there's an option that's 2-sample T interval, it's a capital I. So you would just plug in all that same information. You would say no to pooled. Your confidence interval, if you want 90%, you'd go 0.90 or 0.9 and then calculate. So note that we used a t-star with 17 degrees of freedom. That was our conservative degrees of freedom. In the calculator or in software, it uses this thing called Satterthwaite degrees of freedom. And you'll note it's really gross looking, right? So it's this, the degrees of freedom are 31.59, like it's not a whole number. And that means if you're using this degrees of freedom, you can't use the t-table. You pretty much have to use software to find your T star or p-value if you're using Satterthwaite degrees of freedom. So yeah, you're not expected to use the Satterthwaite degrees of freedom. You can, just know that you have to use software if you do. So where does that even come from? So the Satterthwaite, I always misspell it, always. It's so easy to misspell. It's this entire huge, nasty equation. So you'd have S1 squared over N1 plus S2 squared over N2. You square that, and then you have this whole thing. It's a mess. It's really, really easy to goof up when calculating by hand. It's extremely difficult, which is why most of the time we say, hey, use those conservative degrees of freedom, your smallest sample size -1. It's a lot easier. And not to mention, you can actually use the t-table when you use that. So, can you use the Satterthwaite? Absolutely. Do you have to? No. So, what is that pooled option? So the pooled option, if you select yes, it's saying, hey, we want to assume that the standard deviations of the population 1 and population 2 are exactly the same, and the calculation's a little bit different. It works really well if the population standard deviations are extremely, like if they are equal or really close to each other, it works well. But if they aren't really close to each other, it does not work well. That's why we like to say, okay, well, let's assume that they have their own variances, and that they aren't equal. And then the unpooled or not pooled works pretty well. And if sigma 1 and sigma 2 are equal, the not pooled works well. If sigma 1 and sigma 2 aren't equal, the not pooled works well. However, pooled only works well if they're equal. So using not pooled is just a better option. Now that we have the software for it, I would go with just saying not pooled or pooled no. It's the better option. It'll give you better, more consistent results. So the 4-part conclusion. So remember, this is the 2-part conclusion for the hypothesis test combined with the 2-part conclusion for the confidence interval. So filling in the blank. So we blank the null hypothesis with a p-value, with p-value between, I'm going to say even, just greater than 0.20, right? Because it was between 0.20 and 0.30, with a significance value level of 0.10. So given that, I have a huge p-value. So it's saying, hey, if it really was, if that difference in means really is 0, what we saw in our sample happens kind of often. So we don't have good evidence that that null isn't true. So we fail to reject. And then we have, so I have this written up a couple of ways. So the first one is saying, hey, there's blank evidence there's a difference in the mean weight loss between the participants in treatment A and treatment B. This one, it's a little, I tend to prefer the second way because it's easier to say anytime it's not just that there's a difference, but specifically one is higher than the other. So little to no or weak evidence, because the p-value is so big. So there's little to no evidence that the mean weight loss between participants in treatment A is different than the mean weight loss of the participants in treatment B. So different than, I could replace this with greater than or less than in a different scenario. Versus it's harder to just replace the word difference if you have a one-sided test. Which we don't, but if you wanted to write it up for a one-sided test, it'd be easier to modify this second way. So then I have to write up my confidence interval. So with 90% confidence, the mean weight loss of treatment A is estimated to be, and here's where it's super important to remember which one's higher or lower. So we said it was estimated to be between 10.73, right? 10.57. 10.57 pounds. So this was a negative, so less than, because it was negative, to 2. 1.97 pounds. This was positive, so greater than the mean weight loss in treatment B. So then our point estimate. So what was the difference in means we actually saw in the sample? With a point estimate of 4.3 pounds. This was negative, so it was less than. Less than the mean weight loss of treatment B. So this would be our 4-part write-up. So here's another example, totally unrelated. We have researchers at a pharmaceutical company. They are looking at a new sunscreen formula. So they have 2 formulas. They have an old formula and a new formula. So what they do is they take a bunch of individuals and they put the old formula on one arm and the new formula on the other, randomly choosing which arm goes on which. So what type of problem is this? Is it matched pairs or is it 2 independent samples? So in this scenario, I mean, we're doing in a scenario where we're dealing with 2 armed individuals. It's going to be matched pairs. If I have Formula 1 and Formula 2, how my right arm reacts is related to how my left arm reacts. So it's going to be matched pairs. That my left arm is matched exactly to my right arm. It's not matched to somebody else's right arm. That kind of idea. Another example, we have a National Park Service. They want to compare the amount of money spent by visitors in 2 different national parks, specifically, hopefully, 2 national parks that aren't very close to each other, because there are some national parks where people could reasonably visit them in the same day. So they went ahead, they took a random sample of visitors on the same day from each park. So Park 1, they took a random sample of park visitors. Same day, they took a random sample of park visitors. So here, the idea is we're not supposed to have any visitors that visited both parks. Exclude those folks. It's going to be 2 independent samples. Because it's not that you have, now if you said, person 1, they visited Park 1 and Park 2, but they spent more here, then you'd be looking at differences. But it's really, really uncommon that you would have a huge group of people visiting 2 parks in one day. So the other example we're going to work through here, we're looking at fabrics. So fusible inner linings are being used with increasing frequency. Basically, when they glue some stuff together to support outer fabrics. And so we're looking at the extensibility. I think that has to do with the stretchiness. I could be totally wrong. At 100 grams per centimeter for, maybe it's grams. I don't know. GM. G is grams. For both, but GM might be something else. High quality fabric and low quality fabric. So they're looking at the extensibility for high and low quality fabric. they went ahead, they took a random sample of low quality fabrics and they took a random sample of high quality fabrics and they recorded this extensibility from both of them. I cannot explain to you what extensibility is. It's not something I truly understand. So, I mean, I think the units are percent, but that's all I know. So, investigators, they want to calculate the difference between low and high fabric percent extensibility and determine whether that difference is significant. Because, well, for starters, high and low quality fabric, they have very, very different costs. So it's absolutely important to them, like, hey, if we can get away with using lower quality fabric or whatever, it cuts costs most of the time. Okay, so in the scenario that we're doing like a 2-sample t-test, or we're looking at 2 quantitative variables, or a quantitative variable between 2 groups, side-by-side box plots are an excellent option. It's not really nearly as useful to have something like a side-by-side histogram because they're not so much of a thing. So side-by-side box plots, a lot of times we'll have it turned so it's horizontal. This is okay as well. So here we have the percent extensibilities for the high quality fabrics and the low. As you can see, the lower quality fabrics have lower percent extensibility. Generally, the higher have higher, but they also have more spread out. They have a couple of outliers that really do increase the spread here. So just using this, we can see the higher quality fabric, it tends to have a higher percent extensibility, but it also has a wider spread. It has a couple of high outliers in particular. If it hadn't been for those couple of outliers, it would probably have a slightly smaller spread. And things to note is just like how much overlap are you seeing between these 2 box plots. These are the medians here, these lines, but if it's roughly symmetric data, the medians and the means should be close. And are they very close to one another? And if you don't have much overlap between the boxes, usually we tend to say, hey, it looks like one's higher than the other. But yeah, so just at a quick glance, looking at the sample data, it does look like the percent extensibilities are higher for the high quality fabric. So what is the mean of the high quality fabric? So this is going back to that page that had all of the percent extensibilities for the high quality fabrics and taking the average. This is not definitely a do in your head kind of thing because there's a good handful of them. So when you do throw them into a calculator, you're going to end up with 1.846. Units, they might be percent. I'm not really sure. I'm going to leave off units here because it's not clear. But anytime units are clear, you should include them. So we want to state, hey, what is the question here? And then start summarizing. So what is the estimated difference between the fabric's average extensibility? So what is the difference? So like even what is the difference between the extensibility, the average extensibility for high quality fabrics and the average extensibility for low quality fabrics? And this is more of like an add-on. Is that difference statistically significant? So basically, do we have strong enough evidence that we'll reject the null here? That's what that's getting at. Statistically significant, it's almost not quite like swearing in stats lately. We're definitely moving away from talking about statistical significance a little bit more. It's something that a lot of other fields are still using a lot. If something's statistically significant, all it means is that you had a big enough difference that you rejected the null. It doesn't necessarily mean that it's a big difference itself. So here I'm going to use these labels. 1 goes with the high quality fabric, 2 goes with the low quality fabric, and plug in the sample data. So the sample means, the sample standard deviations, the sample sizes. Absolutely, these values I did not make up in my head. I threw them in a calculator. So then looking here, I have a sample of 24 for the high quality fabrics. I have a sample of 10 for the low quality. So the degrees of freedom, I'm going to take the lower, so 10 minus 1. So my conservative degrees of freedom are going to be 9. Absolutely, you're going to have a higher
weirder number if you use the Satterthwaite. I tend to not use that. And then my sample statistics, so the observed difference in the sample means, I'm going to use x bar 1 minus x bar 2, so 1.846 minus 1.370. I'm going to get a 0.476. Absolutely, that is the sound of me trying to do math, which always sounds raised at the end of the sentence. So this is my point estimate or my sample statistic, the difference in the sample means that we actually saw in the actual samples. And not only that, it's positive, which implies that on average, the percent extensibility was higher for the high quality fabrics, because 1 minus 2, that's high quality minus low quality. Okay, so now that we've written up the question, we're going to want to identify that parameter. So that's going to be that mu1 minus mu2, so the difference in mean percent extensibility of the high quality fabric and the low quality fabric. I do specify what order I'm subtracting, so high minus low. It's pretty common that we're going to subtract in an order that gives us positive numbers if we can, but we might switch it around sometimes. Sometimes it's just really important to subtract in a certain direction. And then, so the question of interest, it's kind of like a two-parter, like, hey, you know, what is the difference? But also, is there a difference? So for the hypothesis test, we're asking, is there a difference? Is there a statistically significant difference? So we're going to start off, so it's going to be mu1 minus mu2 is equal to 0, because if there isn't a difference, the difference is equal to 0, right? If they're the same, the difference is 0. And then it'll be a not equal sign in my alternative. So note also, across the top, we consider these two equivalent. So if you said mu1 equals mu2, that's the same. mu1 minus mu2 is equal to 0. I tend to like this first one just because that equal to 0, that tells me exactly what that claimed or null difference is, versus a not equal sign. So this means that since it's a two-sided test, we're going to want to have a two-sided p-value. So if we're using a t-table, we're going to find a one-sided p-value from the t-table and we need to multiply by 2. So the significance level, you may have noticed they didn't say what significance level to use, and by default it's safe to go ahead and assume 0.05 in a scenario where they don't include 1. And you're going to see later we'll have a 95% confidence interval, so 0.05 and 95, they go together. So checking our conditions. So did we obtain our samples using a random mechanism? These fabrics were selected at random. From what? I'm not entirely sure. Probably all fabrics, like from a specific batch or day or something. But yes, they were randomly selected. So there's that. The samples are independent of one another. Yes. There are no fabrics that were in the low quality and in the high quality pile. It was just one or the other. So yes, they're independent of one another. The sum of the sample sizes, so it is at least 30, right? Because we had 10 in the one and we had 24 in the other. That's greater than 30, so we'll be okay. And things to note, do we know the population standard deviations? No, we don't. So we have to use t-methods, which we kind of knew already. So all the conditions, I would say, are satisfied here. We can move forward and not feel bad. If they aren't satisfied, we still would go forward, but at the end, we would write a disclaimer saying, hey, this may not apply to the whole population, or hey, we don't know that they're independent of one another, and kind of let the reader decide from there whether or not that invalidates or how it invalidates the results. So calculate the test statistics. So I'm going to need all that same information I plugged in earlier. So degrees of freedom, 9. So this claimed difference, that's just going to be 0. It's almost always 0. It's really rare for it to be anything else. So I'm going to just plug in here. So 1.846 minus 1.370 minus 0. That minus 0 just pretty much goes away. I love subtracting 0. Over square root, so 0.498 squared over 24 plus 0.442 squared over 10. This is really, really easy to goof up putting in the calculator. So definitely if you have access to a TI-83 or 84, it makes this part a lot easier. But we will want this set up. So even if you use that TI-83 or 84, we're going to need to know what values were plugged in where. It can't just be magic box that you put the values in and it spits out an answer. We have to know, like you roughly know how it was calculated. And so then plugging in, something like 2.752. I think it depends on what you have in your thousands place. It kind of depends on rounding you use throughout the calculation. So, but either way, my statistic 2.75-ish with degrees of freedom 9. So I have a t statistic of 2.752 on 9 degrees of freedom. So this tells me which row. So here's 9 degrees of freedom. This is a very, very edited version of the table. So looking here, 2.752 is not there. It's not there. It looks like it's actually right here. So then looking up, my one-sided p-value is going to be between 0.01 and 0.02. Always keep track. The order is reversed. So my one-sided p-value is between 0.01 and 0.02. We're doing a two-sided test though, so that means I need to multiply everything by 2. So times 2, times 2, times 2. So I'm going to end up getting my two-sided p-values between 0.02, and 0.04. And if it's less than 0.04, it's less than 0.05. So there is that there. Things to note too, if we're going to do a 95% confidence interval, so 95% confidence interval, T star, we would use 2.262. I'm not sure if we're going to calculate that on the slide so much as have it in the write-up, but since the table's up here, I thought I'd grab it. So grab our T star, yeah. See, I even have a reminder. So there's our T star for a few slides from now. Or at least one. So now calculate the 95% confidence interval. So we said our T star was 2.262. Our sample statistic was at 1.846 minus 1.37. That was 0.476. So, once again, I like to put parentheses there. My setup here, I can write that 1.846, which we just calculated, minus 1.370, plus or minus. So the T star that I just grabbed from that last slide, so 2.262 times that 0.498 squared divided by 24 plus 0.442 squared divided by 10 and the square root, parentheses. So if we were looking for the setup, or this is what we're looking for. is this whole part right here. We're looking for the equation with the values plugged in. You give us this. This is the majority of like this is the setup, and then the interval itself is definitely worth the point. So speaking of which, it looks like it's 0.114 to 0.838. And note that 0.476, it's smack in the middle of that. It should be exactly in the middle. Like if you average these two endpoints, you should get that. And not only that, this entire interval is positive. So it's all above 0. It implies that, hey, the average extensibility is higher in group 1, so the high fabric, than in group 2. So that kind of supports what we were looking at with our hypothesis test. We had good evidence that, the average percent extensibility was different in the two groups. Not only is it different, it looks like the percent extensibility is higher on average in the high fabric quality. So here's the really long write-up, but I'm going to so here are the 4 parts. So when we say 4-part conclusion, there's these 2 parts that go with the hypothesis test, and then the 2 parts that go with the confidence interval. So it's just combining the two-parters. So we have a null hypothesis with a p-value between 0.02 and 0.04, given a significance value of 0.05. So looking at that, my p-value is smaller. So this is strong enough evidence for me to say, I don't believe the null anymore. So we're going to reject the null. And not only that, so then we have to talk about, well, how strong is that evidence? And if you look at that graph from the first, that spectrum from the first lecture, we would say this is strong evidence. You could say strong, maybe moderately strong. I would say it's strong. It's strong evidence that there is a difference in the average extensibility between the high quality fabric and the low quality fabric. You could also write it, there is strong evidence the average extensibility of the high quality fabric is different from the average extensibility of the low quality fabric. The big thing here is if you write it the second way, if it had been a one-sided test instead, you could just swap out less than or greater than, and that would have been easy to do. It's a little funkier to just replace a word and make it one-sided if you do it the first way. We're totally happy with either way, though. So then with 95% confidence, the average extensibility of high-quality fabric is estimated to be 0.114 higher, because it's positive, to 0.838 higher than the average extensibility of low-quality fabric, with a point estimate of 0.476 higher. And I would put units, but I am really unfamiliar with the percent extensibility. We're going to not go there. So then the low quality fabric. So this would be my 4-part conclusion. So the first part is saying whether we reject and why. So basically, what was our significance level and what was our p-value. The second is saying, hey, we have, this level, like this strength evidence for, and then you actually have to translate the alternative hypothesis into like words and context. Then there's the confidence interval, and then the very last bit here is the point estimate. So tell us what you actually saw in the sample, or the samples. So we saw a difference in the sample means of 0.476 higher in the high quality fabric than the low quality fabric. So then one last thing to talk about is robustness. Robustness with t-procedures. Basically, if we're not meeting all of the requirements or the conditions, is it still going to be a reliable test or procedure? So in general, if we know that the sum of our sample sizes is less than 15, we need to know that those samples came from normally distributed populations. So we need to know that the populations are pretty normally distributed. They're nice and symmetric with a peak in the middle. It's going to be really, really messy if you have a sample size of 4 and 5 and you know they didn't come from normal distributed populations. It's going to be a mess. You're not going to like that. Some of the sample size is at least 15. So in general, the t-procedures are going to work well unless you have really strong skewness or outliers. So if you have a sample of like 5 and a sample of, 9, or no, at least 15. So a sample of 5 and a sample of 12. It's going to be okay unless you're seeing some serious skew or some serious outliers. With samples that small, it still can be really problematic. So you want to make sure that, they look mostly okay. And then our really, really happy place is the sum being at least 30. So if that sum is at least 30, we can say, hey, central limit theorem is going to kick in. It's going to be good. Even if you have very skewed distributions or you have distributions with extreme outliers, if you have big enough sample sizes, it's going to be okay. Definitely the sample sizes, they don't have to be equal, especially if they're big. However, definitely, squint at scenarios where, I have a sample of 100 in one group and a sample of 5 in the other. That should definitely make you very wary. It makes us very nervous when we see that. A lot of problems tend to come from that. So you don't want them to be extremely lopsided when it's avoidable. But as long as, you have at least 30, it's usually going to be good. Just make sure they're not super lopsided. That's kind of important. It's a really weird thing when it comes up like that. And I think that's going to be it for this lesson. So I look forward to talking with y'all on the discussion boards.